The Presidential Colloquium, an annual event that celebrates outstanding faculty members showcasing their research and creative work in formal-style lectures. This year's honoree is Dr. Eric Meyer, an associate professor in biomedical engineering and the director for the Experimental Biomechanics Lab.
Eric, I'd just like to express again my gratitude to our keynote speaker, and thank you so much for everything you did. And I just shared with her my own experience. I have been here for a long time. When I came here, there was no research. There was no graduate programs, nothing, zero, zilch. And through National Science Foundation under RUI, I was able to get millions of dollars. But what I found out, actually I learned more from the students than the students learned from me. I mean it. And I figured out for every research project I did under National Science Foundation, the more time I spend with the students, the more I got out of it. If I put 10 hours a week, I get 10 hours a week from them. I get them excited. And based on that, I went to the dean, I went to the provost at that time, I said, we need to develop a graduate program. And we started a master's degree and a PhD, but definitely working with undergraduate was fun. And actually, some of them now are professors somewhere, and we communicate. But certainly, if you give them enough time, you benefit more than them. I thought just share that with you. Having said that, now it's a pleasure and honor to introduce a colleague here, Dr. Eric Meyer. And just for your information, the way it works for the Presidential Colloquium, each dean will come up with a recommendation. And each dean, during the meeting with other deans, will present who should be and why. You don't argue, you don't fight, but you have a strong case, it will go through. So with Eric, it was easy case. So that speaks volume. I presented everything that I believed in him, and I have been watching him for years, almost 10 years. And I remember very well when he came to knock on my door and say, hey, Nabil, can I use equipment in Simmer? So I said, what are you going to do in Simmer? He said, I'm going to test bones. And that attracted my attention more. So I watched him with his students testing bones on my machine. And then after that, I met with one of his funding. I believe he was a dentist. And he was working with Eric. He's funding Eric on some research work for implant. Oh, you will talk about it? Wonderful. So when I took that dentist for lunch, because he kept talking and I got more interested. I deal with concrete, I deal with steel, but this guy deals with delicate stuff. So I'd like to learn more about what he's doing, so I heard from his own funding agency. So I was very impressed, and when I presented his case in front of all the deans, it was easy. And then all of them agreed that Eric will be the Presidential Colloquium, and then we took it next step to the provost. It was easy sell. He took it to the president. And with this being said, please allow me and join me in welcoming our keynote speaker today for the Presidential Colloquium, Dr. Eric Meyer.
Thank you. It's actually been almost 13 years. So thank you, Dean Grace. Thank you, Matt Cole. Thank you to the audience for being here. This means a lot to me. So I have to start with my dad joke. Why did the old man fall in a well? He couldn't see that well. I actually got that joke from ChatGTP. So my idea for this presentation was to ask, what does the future of humanity look like from the perspective of biomedical engineering? So disruptive biotechnology. I wanted to start my story with this painting, The Garden of Earthly Delights by Hieronymus Bosch. You can see in the outer panels that it depicts the earth as a glass vessel. This painting was a triptych format, which was common for the time period and meant to be placed in a cathedral in the Netherlands about 500 years ago. So when you open it up, this is what the inside panels look like, and it depicts the classic religious story of paradise on the left, the fall of man in the center, and hell on the right. But what fascinated me about this painting and caused me to write a 15-page term paper about it during my study abroad was the alternate symbolism that used a lot of alchemy symbols and imagery. And this was a medieval science that clearly the painter was engaged in. The primary goals of alchemists were to transmutate base metals into gold and to create the elixir of life and become immortal. While the first goal has been accomplished by modern physicists using particle accelerators, we're still working on the second goal. So I wrote that essay during one of my favorite classes in art history, favorite classes as an undergrad, because we got to travel around Europe looking at historic cathedrals and museums. And that semester changed my life because it gave me the motivation to go to graduate school. So if the students in the audience, it was a great experience. If you have the chance to study abroad, do it. It will change your life. Oh, sorry, these are pictures from Leuven. So before we discuss how to create the elixir of life, first we need to know if we should. Last week, I was asked to participate in a survey from the sociology professor in UC San Diego, and I thought some of the questions were fascinating, so I wanted to share them with you to get your opinions. So in the future, scientists may be able to give people enhanced abilities. Please indicate the extent that you agree or disagree with the following statements. Make people need only 4 hours of sleep per night. Make people immune to infectious disease. Make people have healthy life for 140 years. Give people greater intelligence than humans have now. Make people much happier. Or give people greater physical strength. So reflect on these. You don't need to provide your answers or reasons. I just think that there's interesting social and ethical questions that biomedical engineers are engaged in. My one criticism might be that I'm not sure it's just scientists that need to be involved in these solutions. I think that there's many other contributions from other professions that make this idea interesting. So as I go through my talk, I want to share personal examples and thank important people in my life. This is my grandfather, Donald Meyer, who lived 97 years. And I learned a lot about life and death from him. Not only did he instill my love of Ireland and St. Patrick's Day, but he got to know my children. And I never knew my great-grandparents, but I did get to spend a lot of time with my grandpa, especially late in life when he was in assisted living, and even as he took his final breaths. So he had arthritis in his knees that caused a lot of pain and restricted his movement until he got joint replacements. He also had dentures, which he hated, and he always wished that he could get dental implants. And those are some of the research topics that I worked on, so I was interested to hear from him and really get that perspective. So jumping back to the life extension myths, there are many versions of this throughout culture and history, and I think it's an important crossroads between the humanities and STEM. And the innovations that we develop should be collaborative. This is a recent example of the social discussions that might occur on popular media. Do we really want people to live 150 years? I think most people react negatively to this initially, but perhaps once they realize that these wouldn't be extra years of suffering, but instead they could maintain their productivity and they could extend their health span, they might be more supportive. I know that I would have wanted my grandfather to avoid the suffering that he had. Another argument is that the Earth cannot sustain a human population if people live longer, but actually our birth rates have been declining for a century, and underpopulation might be a problem in the future. So these possible disruptions from a biomedical perspective have other disruptions that have occurred throughout history that we might be able to learn from. So one example that's related to Lawrence Tech is Henry Ford and the Model T. So the assembly lines produced 15 million cars, which allowed regular people to replace their horse-drawn transportation with the first mass-market automobile. In 1932, the Lawrence brothers established our institution at the Ford factory in Highland Park to focus on technology innovations and train assembly line workers to be engineers. Another example I'd like to talk about is the 2007 unveiling of the iPhone by Apple. There are now almost 7 billion similar devices in the world, allowing everyone the ability to connect and access information. So a little bit about my background. I grew up in Oakland County, just like Lawrence Tech. I went to Ortonville Brandon High School, but I also attended a charter school for math science technology called Awesome Tech. And two of the teachers that had the biggest impact on my career to go into biomedical engineering were there, Mrs. Kyle Hughes and Mr. Mike Olson. They were the founders of the school, and they continue to teach at what is now called Clarkston Science, Math, and Technology. So you can see one of the group projects that I did. After high school, I went to Michigan State University. They didn't have a program in biomedical engineering, so I did engineering mechanics, which is like applied physics. And I did some pre-med courses and got a minor in biomechanics. The other defining feature of my undergrad, in addition to study abroad, was playing club volleyball for 4 years. When I came back from Belgium, I was focused on getting into a master's program, which eventually led to a PhD in mechanical engineering, while doing applied research in the College of Osteopathic Medicine in orthopedics and sports injuries. Then, so this is a picture that includes my advisor, Dr. Roger Hout, which I owe a lot of training. Starting out as a senior, I did an undergraduate research project with him in his lab that then progressed into a master's degree. And also I want to point to Mr. Cliff Beckett in the middle there. He was the technician in the lab, and he just died this year, but he was the one who spent all the hours with me and really helped me set up all of my research and taught me how to use all the equipment. So when I came back, then after I finished my PhD, my family and we moved to Ireland for a couple years, and I did a research fellowship at the Trinity College in Dublin. And that was on cartilage tissue engineering. So I'll briefly talk about some of those aspects of my research. And this was our group. I love the Irish, and hope to one day go back there. And I'm sure my wife agrees. So one of the biggest reasons I went into biomedical engineering was motivated by science fiction and the modern mythology stories around cyborgs. So these are very advanced prosthetic devices that work with the human body, like in Terminator 2 and Star Wars. And this is what I thought biomedical engineers did. Another example, if I can get this video to run, are advanced prosthetic devices. So this is Marcus Rame, and he has the longest jump of any currently competing athlete, able-bodied or Paralympic. And he's pretty unique because he's one of the only people, he was the first to jump off of his prosthetic leg. So that leg has been optimized for storing and releasing this energy, which helps him propel him to such a long distance. I had a summer internship working at Wright and Philippus, and I thought I would be developing orthotics and prosthetics, but I learned a lot working in the fabrication lab, but I realized it wasn't biomedical engineering. The other thing I realized is one of the main groups of people who need amputations are diabetics. So this is caused by complications due to poor blood flow and neuropathy in the later stages. And these patients really don't have good outcomes. So I was kind of discouraged by that. On the other hand, recently I've been more fascinated by diabetes and the advanced treatments. So this is a biotechnology development that used recombinant DNA in the first genetically engineered product from Genentech in 1978. Originally, insulin was available from animal sources, but a lot of patients developed allergic reactions, so what they really needed was a human insulin. And this was accomplished by gene splicing into E. coli, which produced the protein, and then that could be collected and refined into a drug. So another issue for these patients is controlling the amount and timing of the insulin that they inject. Modern insulin pumps solve that problem by providing continuous insulin in customized dosage 24 hours a day. Another historical example of biotechnology is that of brewing and other food production like bread, yogurt, cheese. So yeast are used to convert sugars, or bacteria are used to break down proteins and fats. And humans have been using these technologies for thousands of years. Stella Artois is a brewery in Leuven, Belgium, which has, as you can see there, has been around since 1366. So living in Belgium, I was blown away by the history. The tools available for genetic engineering have gotten even more powerful with CRISPR-Cas9 and other recently developed gene editing techniques. I wanted to share a couple interesting papers here that kind of relate to the theme of my talk. And I also encourage you to read a popular book by Walter Isaacson, The Biography of Jennifer Doudna, to learn more about how these developments impacted and accelerated COVID-19 vaccine development. So at Lawrence Tech, I founded the Experimental Biomechanics Lab, and this slide shows some of the topics that we're engaged in. I'll be sharing some of these throughout my talk, but I'm not going to focus on the hardcore research results. So instead, I would encourage you to go to our website, or I like using Google Scholar, where you can find a complete list of our more than 40 peer-reviewed publications. So I also want to tell the story of the biomedical engineering department. We've been around for over 15 years, and I think we've accomplished a lot in that time and done a great service to our students and to the university. So I want to thank all of our alumni and the current students as well as my great colleagues, our chair, Dr. Yawen Lee, Dr. Michael Lancina, our awesome assistant, Olivia Thompson, thank you, Professor John Paponas, and Dr. Hao Zhang. Thank you all for your work and support. Thank you. So cartilage is one of the tissues that I've been interested in, as it's quite troubling from a disease and treatment perspective. It doesn't have a blood supply, and there's not very many cells. So it can't repair damage or regenerate once the process of arthritis has started. The treatments available for cartilage are nowhere near as effective as what we have for ligament tears or bone fractures. And one of the ideas that we had at MSU was we could save cells after you have an injury near your joint. So we came up with a method that we could save about 50% of the cells, which would have long-term outcomes at preventing degeneration. These are some of the colleagues at MSU in the Orthopedic Biomechanics Lab, and I owe them a lot as well. In Trinity in Ireland, when we were trying to do cartilage tissue engineering, we used mesenchymal stem cells. So you can see pictures that I took there, a couple different phenotypes. Actually, the one on the right is incubated in a low oxygen environment. So that was one of the things that we studied. So we combined these stem cells with hydrogel to create small cylinder discs that we would then culture in a lab for about 6 weeks to see if we could get a functional tissue. The biochemical stimulation we provided included steroids like dexamethasone and growth factors like TGF-beta3 and IGF. We also provided different types of mechanical stimulation, such as 10% strain with this actuator that was put into our bioreactor, or 10 megapascals of hydrostatic pressure, which we applied with that pressure vessel. And 10 megapascals is a huge amount of pressure. It's like more than 100 times the pressure that's pushing down on you right now from the atmosphere. But this is common in your joints. Anytime you stand up or walk, these forces actually help develop the tissue and maintain its health. So we also applied oxygen in our culture environments, or we controlled oxygen. And that turned out to be really important for producing cartilage with stiff and strong properties. And to get the glycosaminoglycan content, which is shown in blue, or the type 2 collagen, which is shown in orange, that we really wanted. And again, this could be related to the fact that cartilage doesn't have a blood supply, so it has very low oxygen normally in the tissue. So this is my postdoc advisor, Dr. Daniel Kelly, in the middle. And I was lucky enough to visit them again. They hosted the World Congress of Biomechanics a few years ago. That's when this picture was taken. And also I worked with Stephen Thorpe. He was a PhD student at the time and is now at University College Dublin. University College London. So the other story I like to tell is about impact biomechanics and our local contributions in the Motor City. So most of you are probably aware of the safety systems that are in modern vehicles, such as airbags, seatbelts, crumple zones, reinforced cabins. In order to design these systems, engineers needed a way to measure the forces on drivers and passengers and understand how injuries happened. They couldn't do these experiments with living people, so they made crash test dummies that have the correct sizes and behave like a human body during these crashes. They're also instrumented to measure the forces that the driver or passenger would experience, and these efforts have made modern cars much safer, at least until recently when we've had more distracted driving fatalities, unfortunately. So this is a picture just a month or so ago of our student chapter of the Biomedical Engineering Society. They organized a tour to go to Humanetics, where we have 3 of our alumni working as engineers. And Humanetics supplies all of the crash test dummies worldwide, and it's one of the local companies in the area. My PhD dissertation started out focusing on impact biomechanics, but I was interested in injuries in sports more than I was in auto accidents. So in this video, you can see Jason Gatson. He tore his anterior cruciate ligament, the ACL, twice during jump landings. And the second time, he was even wearing an injury prevention brace. Fortunately, this story has a happy ending, as Jason went on to compete in the 2004 Olympics in Athens on his reconstructed ACL and didn't suffer another injury. So you can see the very large forces during these activities. So I used impact biomechanics to study the anterior cruciate ligament as well as high ankle sprains. In sports, these are frequently due to non-contact situations where a player is in a compromising position like a jump landing. The ground reaction forces are many times the body weight, and then you also have the muscle forces that are required to keep your body upright. And all of these are pointed in the same direction. So by Newton's third law and static equilibrium, we have to have an equal and opposite reaction in the knee. And this can be 10 to 15 times your body weight. But the tibial plateau is not flat, and so this creates a shearing effect that can damage the ACL. At Lawrence Tech, I wanted to try to prevent these types of injuries. So one approach was to have athletes use a knee brace. But in our design idea, we wanted to focus on compressive loading rather than a traditional injury prevention brace, which restricts hyperextension or valgus bending. So our brace was designed to shift the compressive load from the lateral side of the knee, the outside, which is less stable, to the inside of the knee, which is more stable. But athletes don't like wearing knee braces. They're uncomfortable, they can affect their performance. And so another technique is to do injury prevention training. So from a research perspective, we need to understand what are the best biomechanics to be teaching these athletes. And we've worked with the athletic department and the athletic trainers to do some functional movement assessments with some of our athletes, which can then be used to customize training or to track progress of athletes over time. Recent research in the lab has suggested how the position of the upper body affects the knee reaction forces during a jump. When you lean forward, you have a softer landing. But if you're leaning backwards, and especially if you're leaning to the outside and landing on one leg, then those compressive loads are located through the outside of your knee, which is more unstable, and you would have a lower threshold for injury. I worked with Dr. Hamid Vajdani on a dynamic computational model where we could predict the knee reaction forces for a variety of different body positions, and then hopefully in the future use these thresholds to give real-time feedback to athletes if they're in a risky position. And I'm very proud to be a co-author on a number of posters today. They'll be on display in the afternoon session from 2:30 to 4:30. So this is a research project by Brian, who's one of our BME master's students, and he's been using the motion capture system to measure human movements to predict ACL risk. Another student here is Anthony Walsh, who's a certified athletic trainer in addition to being a master's student in biomedical engineering. He works full-time doing functional movement screening on athletes to assess their performance and injury risk, and then develop customized training programs based on that information. But we can't always bring athletes into the lab to do these assessments. They're time-consuming, and most trainers don't have access to a research lab. So Anthony will be presenting his research comparing the error scores with quantification of joint kinematics that we can get from wearable sensors. These sensors are similar to what's in your Fitbit, but we want to place the sensors on all the segments of the body to record all the motions of the athlete. The benefit of these sensors is they're small and light, so they can be worn in real-world settings. And a lot of professional athletes are wearing these during all of their practices and games throughout the entire season. Our sensors also have Bluetooth, so they can stream data directly to a smartphone and give real-time feedback or track changes in motion over time. Another approach is measuring human movement with computer vision. So everybody has a very powerful video camera in your pocket, part of your smartphone. It's actually capable of recording high-definition, high-speed video that could be used to do motion capture. So a new system called OpenCap was developed at Stanford University and released this fall. And this is an app you download on your phone, and then it syncs between 2 and 4 cameras and uses computer pose detection to give you the 3-dimensional motion capture results. So in that video, we set it up at the field house on Wednesday to help the LTU women's volleyball team do some player assessments. And Nicole is another master's student in biomedical engineering who's been designing the system to work with various uses for coaches or trainers, but also for STEM outreach programs that we could teach biomechanics to K through 12 students. So I'm going to shift gears again. In addition to sports injury prevention, what are some of the other medical challenges that biomedical engineers can work on? There's still many diseases and injuries that are important in our society. And what we started doing is beginning our design process with opportunity recognition steps. And these are part of what has been termed entrepreneurial mindset. So that mindset and engineering skill set need to be developed in our students. And we've implemented many curricular changes at Lawrence Tech through the support of the Kern Entrepreneurial Engineering Network, or KEEN for short. So Lawrence Tech has been one of the longest and most active KEEN partners. And we had a very strong showing of faculty who attended this year's annual conference in Atlanta. So shout out to you guys as well. I also want to thank Dr. Andy Gearhart and other faculty who have been leading faculty workshops as part of KEEN that train engineering professors not only in the entrepreneurial mindset, but broadly more of the best practices for education, like active collaborative learning. These can also include modules like problem-based learning, project-based learning, product-based learning, and recently I've been interested in simulation-based learning, which has been applied for a long time in high-risk fields like training pilots, and more recently in medical professions, we have a new health science college here at Lawrence Tech, and they have simulation labs in nursing, physician's assistant, and cardiovascular perfusion. And then another shout out to the Keen Network, and particular Doug Melton, who's the program director, and he's been supporting us for a long time. So our approach has been sort of a learn by doing approach. These show 3 examples of EKG monitors that kind of record your heart rate. On the left is a breadboard circuit, and this is what Professor Proponis uses in bioinstrumentation lab to get students to learn how to build and analyze circuit designs. On the right, on the other side, is a commercial EKG monitor, and this is a FDA-regulated medical device that now has been miniaturized and built into a lot of smartwatches like the Apple Watch. But the problem with learning from these devices is it's really hard to see how they work. You can't really take them apart and understand the science and engineering. Another problem with both of these approaches is they're difficult to make changes. If students want to modify these for a specific design project, there's no easy solutions. So in the center is an open electronics kit. This uses Arduino microcontrollers and plug-and-play EKG sensors that can be programmed with computer code to do the specific applications. So students can easily use these resources in their senior capstone design or other projects that they're working on. And we wanted to give students more experiences with these kinds of open electronics and programming to get them comfortable throughout their curriculum. So this is an example of a gyrometer. This was used to build a swing sensor like for baseball, tennis, or golf. And we used the entrepreneurial mindset to motivate this design project in my biomechanics class. We even brought in the LTU softball coach one year. She gave the students a hitting lesson so they would better understand the swing kinematics. And we even used the coach as a customer for the product so that students would be able to think about and develop a more useful solution for this opportunity. Another example is from my orthopedics elective, and this is Dr. Pat Atkinson from Kettering University, who I've worked with to share similar modules for our classes. So these use the entrepreneurial mindset as well as simulation-based learning to introduce various surgery applications and the orthopedic implants and tools that surgeons use. The students start by building their own lower extremity from these models of bones and adding all the soft tissues, muscles, skin, blood vessels, and so on. And this is a different approach to learning anatomy. So rather than dissecting cadaver tissues or memorizing out of a textbook, this is more of an engineering approach to build it. And then we break it. And then we fix it. So that's interesting, important part of engineering. So a lot of the tools are just off-the-shelf drills and saws from Home Depot, but this is actually how orthopedic residents are trained starting out. You wouldn't want a surgeon to just go in and practice operating on a live patient. So they work with these models first and then go to cadavers or animal tissues before they assist in surgery. So we had Exploration Day a couple months ago, or a month ago, and we do ACL reconstruction surgery with the high school students. They get to do this on these models of knees. And this year was particularly fun because both my son and daughter were there. So this is my son Nolan in picture. I hope they enjoyed it. We've also partnered with medical device industry, and this is an example of a local company that makes spinal fixation implants and the surgical tools to go with it. When you have damaged intervertebral discs, like a herniation, that tissue needs to be removed, and then you replace it with bone graft. This allows the vertebral bones to fuse together as they heal. But while the bones are fusing, you provide spacers and screws and rods that provide stability during the healing process. So the other reason this system is great is because these are the actual tools used in surgery. So students get a real hands-on experience with that. And then we've even done some research with the company to help validate ways to make these tools arthroscopic, so they would be more minimally invasive during the surgery. Dr. Stephanie Rossman got her PhD from Lawrence Tech a little over a year ago in mechanical engineering. She built this finite element model of a lumbar spine and used it to understand how intervertebral disc herniations happen due to bending and compression on the spine. She also modified the model's anatomy similar to certain types of surgery, like a laminectomy or a facetectomy, where they remove part of the vertebra. And looked at how this affects the intervertebral disc forces during these types of loading. And what we found is doing these surgeries actually disrupts the muscle forces in the back of the spine, which can cause long-term problems for degenerating disc disease. So this is Dr. Rossman getting her PhD diploma. Another research project that I worked on that Dean Grace mentioned is with the dental implant industry. So Versa was started by a periodontist, Dr. Salah Huwais from Jackson, Michigan. He invented a new method for placing dental implants. So in the past, dental implants are inserted by first drilling out a hole in the bone to create space. But in low density regions of bone, like the posterior maxilla, this reduces the implant stability as you're removing the bone tissue. So his idea was to preserve and improve the mechanical properties of the bone by compacting it to create the hole instead of extracting it. And you can clearly see the dense layer of bone around the farthest column there in our x-rays and histology slides. So we did this validation study compared to the traditional methods at the Center for Innovative Materials Research. And then we published our results in the International Journal of Oral Maxillofacial Implants, one of the top journals in the field. Since then, Dr. Huwais has started his company, and it's been going like crazy. So he travels around the world teaching clinicians how to do this procedure, and the Versa tools are in thousands of dental offices and have been revolutionary for certain types of dental implants procedures. So I'm going to shift gears again. Recently, we've been focused on wearable technologies, like the sensors I mentioned for Anthony's study. So there's a variety of different sensors that could be worn and could be used for design projects. So often, we're focused on creating consumer products, but the same sensor would be used in a medical device as well. But the benefit of a consumer product is we can avoid the rigorous FDA regulation that would kind of stifle some of the creativity or solutions that you could create that would impact people's general wellness. And one example of a project like this is from Saul, another biomedical engineering master's student. So he's using EMG sensors in wearable devices to target physical therapy or fitness training. So back to my title theme of disruptive technologies. There have been many biological revolutions driven by evolution and natural selection. And when you look at the timeline, humans have not been around for very long. But we've developed remarkable tools from fire, timekeeping, wheels, agriculture, writing. It's really in the last few hundred years that the industry has accelerated this innovation process. So the first industrial revolution was the textile mills, the steam engines, the mass market products. And then in the early 1900s, we had electricity, motors, the assembly line. And recently, we've had electronics and computers. But we're actually currently in the fourth industrial revolution. So this includes cyber systems, which are connected through mobile and cloud with remote sensors, big data, and then using AI. There's also simulation and 3D fabrication through computer-aided design. And these are the topics that we wanted to focus on when it comes to wearable technology. So we've continued developing our plan with now what is called the Wearable Technology Innovation Center. And we submitted an NSF grant proposal for creating a regional innovation engine at Lawrence Tech. This would merge the Industry 4.0 technologies into wearable systems that enhance human wellness and productivity. Artificial intelligence has been a huge topic of interest this year with many great advancements in generative AI, such as ChatGPT, now GPT-4, DALL-E, and Midjourney. And I was fortunate enough to be part of this panel discussion a couple weeks ago where we talked about our different approaches for incorporating these types of AI into education at Lawrence Tech. So I appreciate being able to share these thoughts with colleagues. So these are some of the wearable senior projects that we've worked on. The first example is actually from Professor Proponis. He had developed an app-based device for carpal tunnel therapy. Another example that I advised was a wearable knee monitoring sleeve. And then there's Bluetooth-enabled sensors for detecting heart sounds and breathing sounds, or temperature monitoring for pediatric patients. And we've encouraged our students, even our undergraduates, to attend and present their work at national conferences. Other types of projects that I'm involved with are contract research projects with industry, or student industry sponsored projects. One example is the senior project group that has been sponsored by Lear for the past 3 years. And this year's team has made great progress towards goals of creating a long-term comfort testing system for automotive seats. And they have a poster here later today as well. So we've also partnered with the Centropolis Accelerator. These projects are with startup companies or other entrepreneurs coming from outside of the university, or in some cases from within the university, student ideas and things like that. And it's been exciting to work on these proof of concept devices with the ultimate goal to create commercial products. And here's another example of a swing sensor, which we hope to bring to the Centropolis Accelerator for commercialization. This includes the motion sensors as well as pressure monitoring sensors in a tennis racket. And that could be used for helping diagnose tennis elbow. So this is from our master's student, Carolyn. So the Wearable Technology Innovation Center has identified 4 social issues we think we can address with wearable technology. So these include construction and workplace safety, youth recreation and sports injury, elder care and supporting caregivers, and general human productivity and wellness. And one example of a project related to these social issues is from Vaishnavi. She's built a haptic feedback system that we want to incorporate into a wearable robotic assistant that would help pedestrians and workers. So the ultimate goal is to help people navigate through complicated environments and increase their awareness of dangerous objects, especially while they're walking across campus staring at TikTok. So distracted walking. And so far we've developed partnerships with 30 local and regional companies, hospitals, nonprofits, and government agencies as part of this proposal. And we'll be continuing to develop these collaborative resources to develop new solutions, support industry, and also train workers to get into the wearable technology design fields. So check out our website, and if you're interested, reach out to me. And I would be remiss if I didn't thank my colleagues. So this is a long list. I apologize if I left people off. Many of my LTU colleagues, but also my colleagues from MSU and from Trinity College Dublin, as well as our students. We have many students, not only the master's program, but also undergraduates and our alumni that have worked on research with us. So to wrap it up, I want to go back to the diabetes theme. Glucose monitoring has been around since the late 1960s, but this often involved finger sticks. And these are needed to be done many times a day to adjust the insulin injections for people with diabetes. More recently, continuous glucose monitors have been shown to be much more effective, but the system started out as very large, bulky devices that were used in hospitals. And recently, the technology has been miniaturized into a small device that's stuck on the skin for a few weeks and streams data over Bluetooth to your smartphone or even a smartwatch. And I feel like this continuous glucose monitoring would have been really helpful for people like my wife's grandmother, Virginia Marquardt, who suffered from diabetes later in life. And she also lived 97 years. She was also very important to us in our lives. She introduced me and my family to Petoskey, which is just north of Traverse City along Lake Michigan. And now we get to spend a lot of time there as my parents have retired there. Continuous glucose monitoring is becoming more of a consumer product. These are medical devices meant mostly for people with diabetes, but now even athletes have become interested in using them to understand their health and nutrition. So an example is Rory McIlroy, who actually wore a CGM at the PGA Championships last fall, which he won, as a way to improve his training and keep his body in peak performance throughout the season. And you can even sign up for these app-based subscriptions that will provide you with CGMs as well as health and wellness support. They're kind of expensive though. The other problem with the current CGMs is they require injecting a small filament under the skin, which is actually what does the glucose sensing. But new technology that could be built into smartphones or other wearable devices might avoid this invasiveness. And it's been rumored that Apple wants to develop these kinds of products for like the Apple Watch. And I've been tracking my own nutrition recently. I even started doing some finger sticks to measure my blood glucose and ketone levels. I'm not sure how helpful this information is to me yet. What I really need is a personal AI assistant that sorts through all this data and tells me exactly when to eat and exercise and what supplements to take. So hopefully we can work on that too. And to tie this all back to the original anti-aging theme, here's a couple recent examples of using hormones or cytokines to treat or even reverse type 2 diabetes. So GLP-1 is a potential target that instead of just treating the disease with insulin, we could actually treat the underlying causes. The other example is from Genentech, which created the original insulin and also synthetic human growth hormone. And they've been working on using genetic engineering to reprogram cells to make them more youthful. So with that, I will conclude that what we really need is the social and ethical issues of biotechnology to be discussed amongst a wider population. So I think this is a really exciting topic. I hope to have a long and healthy life. And I'll leave you with a quick picture of Petoskey. I want to thank my parents, Marcia and Kevin Meyer, for instilling a love of learning, and also to thank my children who are here, Bella, Nolan, Emmett, who hopefully will be Blue Devils soon. And for my next study abroad, I've been dreaming about visiting Mars on the new SpaceX Starship. But I do want to come back and retire in Ireland with my wife, Susie. So even if I don't get to Mars, I appreciate that she was willing to pretend being a Martian with me. Thank you to Susie for all your love and support. None of this would have been possible without you. Thank you. Thank you. And quick acknowledgement to funders and also to the rest of my family. Yeah, if you have questions, I'm happy to talk more.
What a wonderful journey, and a very impressive journey. It's actually a role model to all of us. As I said earlier, I was very impressed every time I see him testing a lot of stuff in biomedical or in my order there. And if you have any questions, please. Yes, please.
It seems like you reinvented what you were doing many, many times, and maybe I just don't know your field well enough to understand the connection between all of them.
I might be a generalist.
But I mean, can you like share with students maybe some strategies for thinking about how to do that?
I do focus very well, but I can't do more than one thing very well at a time. So I focus for a specific thing. Like right now, it's sort of the nutrition and how we can develop wearables to help with that. So kind of go all in on a topic. I'm very future oriented. So I'm just like always thinking about what the next best thing is.
You got a question over here.
Hey, how's it going? So I was around for some early iterations of this talk, so I'm going to throw the easy one.
Yeah,
which
the
is-
original slides were 300
Yeah.
and took me more than 2 hours to present.
Yeah. So I wanted to invite you to maybe talk about something that I know you maybe didn't get to, which is something about how these advances in biotechnology can impact something that you did talk about like potentially retiring on Mars, about sort of the future of innovations required to make life more palatable, on a different planet.
Yeah, one that I really like that I think is sort of within the realm of possibility is right now we need to get vitamin C exogenously. We have to like eat citrus every day or we get scurvy, yeah. So that's a problem because like the old days when people were traveling around the world on steamships, they didn't have access to nutrients, fresh fruit. So that would also happen on a long space journey. So we can modify our genes. We have the gene for making vitamin C, it's just turned off right now. So we just need like an mRNA vaccine and we can just turn that back on.
Any other questions for Eric? Don't be shy. We got some time, a few minutes. All right, Vivian. I'll walk over to you. No, here we go. Come on. Thank you.
Hi, Eric.
Hi.
I was so interested in what you said about your study abroad experience. And it seems like, so you went to Europe and you studied art history. And
That was one class.
That was one class, okay. Okay, so maybe now I'm kind of rethinking my question.
Take art history in Europe. It's
Yes.
better.
So, but it seemed like studying art had a really big inspiration for you, or really was inspirational for you in you choosing your particular path, which was not art history or the humanities. And
I think it was one of the best classes I ever took.
And I'm wondering what kind of inspiration you found in those art classes to send you on your path to science.
I'm not sure how much direct, but the indirect would be just really allowing me time and reading and experiencing to think about what did I want to do for the rest of my life. So that made me decide I wasn't quite ready to go into industry, as a bachelor's, graduate. I wanted to keep going in the academic route. I loved learning, and there were actually like a whole list of degrees I wanted to get. I've kind of moved around a lot with these topics now. But then just figuring out how to move into the next step. It gave me that perspective.
Thank you. That is a lovely answer.
Here you go, Patty. Oh, here you go. Here.
Quick question. Awesome presentation.
Oh, thank you.
I think we're all blown away. And what a beautiful, wonderful family that's so supportive. This was a tremendous presentation. My only question is, where do you get your time?
I listen to a lot of podcasts while I'm driving. My wife does all the work.
Here we come. I'm coming. Excuse me. Pardon me. Pardon me.
Hello, I'm Carolyn. I'm one of the master students working with Dr. Meyer. From the question before, I was wondering, with your study abroad, what was the major differences you experienced, like going to Europe and now like being back in America?
Ireland is not Europe.
Kinda.
So if you're not sure, just go to Ireland. It's kind of like America East. But Belgium was great because they speak 5 different languages there. They have 3 official languages, German, Dutch, and French. But really, everybody spoke English. So most of Europe, you have more trouble as an American who only speaks 1 language. But it was really easy there. And it's also now the center of the European Union. So you have lots of people coming from all over Europe. So I had friends from Germany, from Sweden, from Denmark, England, a few people from the US, but actually mostly I hung out with the Europeans. And so it was great to just have friends from all over. Except for the Belgians. They don't talk to anybody.
I have a kind of a serious question for you. So Dante in the Commedia, it starts saying, in the middle of my life, nel mezzo del cammin di nostra vita, and he means 33. He was 33 when he started the travel to the hell, right? And this means that it was 33. He was supposed to live 66 years, right? And now we don't live 60 years. Dante was in the 1300, something like that. And now we're in 2023, right? And so we live maybe around 85 years. But the last 15 years of this long life, they are pretty kind of difficult, right? And but what you present here is that you want kind of we are already engineering a lot to bring us from 66 to 85 or something. In 700 years, we did miracles in that. So what is your perspective? Where do you want to arrive with your research in this, and do you think it's right?
So a lot of the extended lifespan over the last 100 years has been due to infectious disease. So antibiotics, basically. But that's introduced more age-related diseases. So cardiovascular disease, diabetes, cancer, those have become more common. And those are somewhat treatable, but you can extend people's lifespan with those, but we can't really prevent them. So I don't have a solution for really any of that. But I would say that I do think all the money that's being invested in cancer research or cardiovascular research, they'll find solutions probably. But also just from a general wellness perspective, I think people are really having tools that they can use on a daily basis to understand. So if you wear a continuous glucose monitor on a daily basis, you'll see every time you take a piece of food in your mouth, a spike in insulin. And that's a really powerful feedback for somebody to change their behavior. So that's the approach I'm kind of advocating with wearables, is providing people the tools for knowing more about themselves.
And why?
So they can lead healthier, more productive lives.
So they can work.
Happier. I don't know how to help with happiness.
That headline that said, "We need more people," it's so there's workers.
No, I think we're getting to the point where we'll have autonomous robots that will do all the work for us.
So this is a kind of serious question too. What are your thoughts on the costs, like the pharma industry and biomedical technologies and the benefit to the broader community? How do we solve those problems? Do you have any ideas?
I'm really glad
in
you
that
asked me
space?
that. So I mentioned we can save cartilage cells after a joint injury. This is an injection of poloxamer. It's a surfactant, P188. It's been approved by the FDA. It's safe for treating other forms of necrosis like traumatic brain injury or burns. So it's a very small molecule, hardly even classified as a drug. But if you inject it into the joints within 24 hours of a ACL tear, you can save about 50% of the cartilage cells. So why is that not being manufactured? There's no money for a clinical trial because there's no patent on that. So that's a problem with the pharmaceutical industry. The amount of regulation in the medical field prevents solutions for people's wellness.
Hey, Eric. Very good presentation and very motivated. What will be your key advice to early researchers, students, or the discouragement and the obstacles come through, going through all the journey was very impressive.
Yeah, I think Lawrence Tech is great for undergrad because they can get a lot of these experiences. A lot of, what I experienced at Michigan State was, I called trickle-down academics. They have, the Research One funding professors, but those aren't the ones that most undergrads are experienced with, But going to my lab in grad school, I worked with my PhD advisor on a daily basis, and he taught me how to write and how to think. So it's really finding that mentorship, especially at a graduate level, working with all the other graduate students. That was, what gave me the confidence and the resources to be able to progress.
Well, thank you.
Here, let me get you the microphone. All right, speak loud.
I'll repeat it.
Thank you.
With the iPod, iPad, iPhone, iCloud, iCloud, and everything else. So where do you
I think it's important to have people you look up to. And so I look at great innovators and I try to learn from them and be inspired by them. So no, I would not put myself in any category like that. Similarly with researchers, when I go to a conference and I see an amazing presentation, my first reaction is, holy crap, I could never do that. That's amazing. And I want that. Because then the next day I'm like, I got to do it. So it gives me motivation to have heroes. I think everybody should have a hero that you look up to. Other than their family. Obviously, they should be heroes too.
Well, I think we're good. Thank you, Eric. Are you ready for your out music?